Hello everyone, this video is for reviewing math problem for KTCE whose employee year is 2024. KTCE stands for Korea Teacher Certificate Examination. Anyone who wants to work as a teacher in either middle school or high school in Korea is supposed to pass this exam. This is a nationwide exam. This does not divide public school or private school. Both private and public school who wants to apply for those two schools, they have to pass this exam. For this video, I'm going to specify the math problem, measure B problem, number 7. This is a differential geometry problem regarding Gaussian curvature. Let me first give you a brief introduction of the curvature on the surface. In R3, the surface may be flat like here, or could be vented. For instance, a cylinder here, and the curvature intrinsically measures how much the surface is curved, which means is different from the plane, deviated from plane in a given direction. The direction is important because for the case of cylinder, we can think two directions. For a given point P here, in the first direction, let's call it direction A, the surface is not vented or is not curved on this direction. So in this case, the curvature in the direction A will be 0. But let me think on the other direction here. Let me say it's a direction B. In direction B, the surface is certainly curved, and the information of how much the surface is deviated from plane is the information is contained on the second derivative of the curve on that direction and its normal vector. Those two contains the information about curvature here. So we can think about unit normal vector here at point P, and then we we can make a curve which is unit speed curve. Let's just say gamma of t, such that its starting point is p and its tangent vector in a given point p is b direction. Let's just say b direction. Okay, so its tangent vector, say, should be parallel with b vector, and its length should be 1. Okay, let me draw a picture here. There's some surface here, and we have a point P, and we made a curve passing through this point, and whose tangent vector at point P is in a direction of B here. Okay, and we can think about the tangent plane on this point P here, because tangent plane we can derive it from its uninormal vector here at P, at point P, and the tangent plane will look like this. Let me say this is a tangent plane at the point P. Let me say this is a surface M, and this will be a tangent plane at point P on the surface M here. If this surface is not vented in the direction of B here, and then its tangent vector, the change of tangent vector will be stayed in the same tangent plane. That means if the surface M is vented in a B direction, then its change of tangent vector, its second derivative, which is the second derivative of this unit speed curve, and the inner product with its uninormal vector will not be 0 if it is vented. Okay, let me say that this is a unit speed curve here. We have to reparameterize the curve if it is not a unit speed curve. Okay, so we have to consider the second derivative of this unit speed curve, and so the question is where the second derivative of this unit speed curve lives. From the condition of unit speed, its inner product will be 1, and then by taking another derivative with respect to t here, the curve is already a unit speed curve. Then we have 2 times second derivative of t of gamma t and first derivative of gamma of t equals to 0. That means their inner product is 0. That means the second derivative of gamma of t is perpendicular to the its tangent vector. So since this is an R3 three-dimensional, so we can think another axis at the point P here, which is perpendicular to both its unit normal vector and its tangent vector gamma prime, which will be its exterior product. Unit normal vector, exterior product, its tangent vector here. So the second derivative of this unit speed curve lives here. Okay, so at t equals 0, so this second derivative vector of this second derivative lives in a plane generated by two bases which are exterior product of its unit normal vector and tangent vector when t equals 0 and its unit normal vector. Okay, so in this part the information that how the surface is vented in a given direction is inner product of second derivative with its unit normal vector here. So by the inner product, so this much will give us information. It is called normal curvature. And the other information that which does not contribute to the venting of the curve, how much the surface is vented, but how the unit surface curve is oscillated or just change its direction in the same tangent plane. This much is called geodesic curvature. This does not contribute to the how the surface is vented in a given b direction, but this is more geodesic curvature is more related to the unit speed curve gamma itself. Its geometric meaning is so. So for instance, consider on the plane there's a unit speed curve. On the plane L, there's a unit speed curve who makes circular movement here. Okay, and let me call this point is P, and obviously we have a unit normal vector at point P here, and its tangent vector will be this direction here. And then since this is a circle, this unit speed curve makes a circular movement here, exactly a circle. Its second derivative will be here. So in this case, the inner product of its second derivative with respect to its unit normal vector is 0. However, its inner product with exterior product of its unit normal vector and its tangent vector will be non-zero here. Okay, actually in this case its second derivative is parallel to the exterior product of its unit normal vector and its tangent vector here. Okay, so that will give us how this curve makes circular movement on a tangent plane. So this is not relevant to the how much the surface is curved, okay, or vented. Okay, so in the unit speed curve case, the norm of its second derivative gives information of curve, so it is called a curvature here, curvature K, and we can separate this curvature into two parts here. One is its inner product of its second derivative with its unit normal vector, its normal curvature, and the other one is called the geodesic curvature. So we have this information from the unit speed curve and the norm, square of norm of its second derivative. Okay, so anyhow, the point is to figure out the information of curvature, we have to set the unit speed curve which passes through the given point here. In this case, this will be this point, square root of 2 comma 1/2 comma 1/2, and we have to find its unit normal vector. Okay, let me directly dive into the problem. Surface M. In this case, this surface M is rather special because it's a surface of revolution. That means this surface is obtained by rotating some curve, and then from the equation you will have 4 times y square plus 4 times z square will be 4 minus x square, and y square plus z square will be 1 minus x squared over 4. This is an equation of circle whose radius is square root of 1 minus x squared over 4. Let me draw a picture here. In this case, I will set x-axis on this direction and xyz direction. And okay, when x is 0, this will be 1. So it will be a circle with a radius 1. Okay. And when x is 4 times square root of 5 over 5, this value will be 1 minus 1 over 5, 1/5, 1 minus 1/5. No, it's 4 over 5, so which will be 1/5. So in case of when x is this is 4 over square root of 5. 4 over square root of 5. It will be a circle, but its radius will be 1 over square root of 5. And the surface will look like this. Okay, actually it will cover the whole angle, but from this restriction gives us this is a line of z equals square root of 3 times y, and the angle of this one is pi over 3. Okay, so actually the surface is restricted by the plane which is z equals square root of 3 times y. So this plane will cut the surface of this part away. And since this is a surface of revolution, I can parameterize the surface capital M with some variable here. First, this line generates this curve when z equals 0, generates this surface of revolution. So when z equals 0 here, it goes away. What we have is y squared equals to 1 minus x squared over 4. So the surface capital M can be parameterized as x comma y coordinate will be square root of this one. So y coordinate will give us this radius here, y coordinate, and we rotate this one with the angle of theta here, and then times cosine of theta, and 1 minus x squared over 4 times sine of theta. So the surface of revolution M is parameterized with two variable x and theta here. And also, since this surface is generated by this curve, so instead of the point here, which is square root of 2 comma 1/2 comma 1/2, instead of this point I will figure out the curvature of this point, which is square root of 2 comma when x is square root of 2, the y coordinate will be 1 over square root of 2 and 0. Okay, so let me say this point is p prime. Okay, the second thing is to find unit normal vector. On the curve, say y equals this generating curve 1 minus x squared over 4 here. Since we parameterized this surface capital M, we take a partial derivative with respect to x and y simultaneously, and we'll have 1/2 times 1 minus x squared over 4, and its denominator will be minus 2x over 4 cosine of theta, and its z coordinate will have the same x part and times sine of theta. And for the partial derivative with respect to theta, let me emphasize that theta is this direction here. Theta changes, it's a rotation, so partial derivative of theta is this direction here, which is YZ plane. Will be 0. Derivative of cosine is minus sine 1 minus x squared over 4, and derivative of sine will be cosine 1 minus x squared over 4. And then by taking a exterior product of those two partial derivatives, we'll have information of normal vector field on this curve y equals square root of 1 minus x squared over 4 and z equals 0. By taking a partial exterior product of those two, let me first cancel out those two in the denominator and numerator, and we'll have square root of 1 minus x squared over 4s are cancelled out, and what's left is negative x over 4. And for the y coordinate, we'll have minus square root 1 minus x squared over 4 times cosine of theta, and for the z coordinate, we'll have minus 1 minus x squared over 4 times sine of theta. And since those three coordinates all have negative sign here, let me change its sign to positive here, so it's outside of this direction. Let me call it normal vector field x comma theta here, and we want to normalize this normal vector. So by taking its square of norm, we'll have x squared over 16 plus 1 minus x squared over 4, which is 1 minus 3x squared over 16. So its norm of normal vector field is square root of 1 minus 3x squared over 16. By dividing all the side, all the coordinates by square root of 1 minus 3x squared over 16, we'll have unit normal vector field, which is x over 4 times square root of 1 minus 3x squared over 16, and then square root of 1 minus x squared over 4 over 1 minus 3x squared over 16 times cosine of theta, and square root of 1 minus x squared over 4 over 1 minus 3x squared over 16 sine of theta. This is our unit normal vector. This is a general case. Actually, when z equals 0, which means theta equals 0, so we can plug theta equals 0 into this theta here, but let me put on this way. And the second issue, the third thing is to find the basis for the tangent plane. Find the here I'm gonna looking for orthonormal basis of tangent plane. More general case is on the curve y equals this is a generating curve 1 minus x squared over 4 and z equals 0 here. The reason why I'm looking for the orthonormal basis, I'm gonna tell it later, but it makes our lives easier once we got this orthonormal basis. And by the virtue of the surface of revolution, those two partial derivatives are already orthogonal. They are perpendicular to with each other. So I'm gonna take those two as our candidate of the orthonormal basis. So what is left is to normalize those two vectors. Then I will have 0 minus sine and cosine in this case. And for the partial derivative of x, I'm gonna have, as we have already done, the norm of this partial derivative with respect to x, which is square root of 1 minus 3x squared over 16 over 1 minus x squared over 4. So it's normalized vector will be inverse of this. So square root of 1 minus x squared over 4 over 1 minus 3x squared over 16. And for the second coordinate, we'll have minus x over 4, and those square root of 1 minus x squared over 4 are cancelled out, and what's left is square root of 1 minus 3x squared over 16 on the denominator, and we multiply by cosine here, and by the symmetry we'll have x sine of theta over 4 times square root of 1 minus 3x squared over 16 here. So by the virtue of the surface of revolution, I could easily get the orthonormal basis of the tangent plane on this generating curve in general. So let me call it the u1 vector is 1 minus x squared root of 4 over 1 minus 3x squared over 16 minus x cosine theta over square root of 4 times square root of 1 minus 3x squared over 16 minus x sine of theta over 4 times square root of 1 minus 3x squared over 16 here. And u2 vector will be 0 minus sine and cosine. So I get the orthonormal basis for the tangent plane on this generating curve here. Here is x comma square root of 1 minus x squared over 4 comma 0 here. Okay. The reason why I found the unit normal vector field in more general case for every theta here is for figuring out the value of total Gaussian curvature. We have to take integration on this whole the surface on this domain, and once we know its Gaussian curvature capital K on this generating curve, and then the rest of the Gaussian curvature following this line by just this curve getting, which is given by just rotation, by rotating by theta degree, we'll have the same Gaussian curvature K value, so we can generate its Gaussian curvature K value on this whole curve, which means we can expand this value on this whole surface. Okay, so the last thing is to find the value of the shape operator. Actually, it is more related with directional derivative. Let me say shape operator L. The shape operator L in the direction, say, let's say B direction here. B direction. The the point should be specified. So the shape operator at point P prime, I'm gonna find its Gaussian curvature at the point P prime, which is square root of 2 comma 1 over square root of 2 comma 0 instead of this point P here, because their Gaussian curvatures are the same. In the direction of B is nothing but directional derivative of each unit normal vector with respect to B direction, and we put a minus sign on it. For the directional derivative, it's a derivative of this unit normal vector following some curve, which is a unit speed curve, let's say gamma of t, which passes through point P prime when t equals 0, say. Okay, and its tangent vector gamma prime when t equals 0 it should be B direction, since it has a unit speed, so it's a normalized B vector here. So you can think that unit normal vector field on this curve here, on this unit speed curve, and then you take a derivative of this unit normal vector field, and then you will have this unit normal vector field is on this unit speed curve gamma of t, and we take a t derivative here and we evaluate at t equals 0, and there is a minus sign here. Okay, so this is the meaning of the directional derivative. What I'm going to do is I want to find the value of shape operator more general. Let's say this generating curve is g of x here. Direct shape operator on the point of this generating curve g of x here in the direction of one of our orthonormal bases u1 and the other one u2 direction. It is known that the result of the shape operator is lies on the tangent plane at P prime here. So since u1 and u2 are bases of orthonormal basis of tangent plane at the point of g of x here, it will have a linear expression with respect to those two bases. Okay, so I want to figure out its coefficient. And by the way, for the case of orthonormal basis on this generating curve here, when z equals 0, which means theta equals to 0, so we can apply theta equals 0 to into the theta value here. So we'll have 1 here, and we'll have 0. So this whole z coordinate will be 0. And for the u2 basis on this generating curve, 0, 0, and 1 here. So okay, so let me simplify those values here. Cosine of theta is 1 when theta is 0, and sine of theta is 0 when theta is 0. So this will be enough for our orthonormal basis on this generating curve here. Okay, and for the shape operator in the direction of u1, by the virtue of the surface of revolution, this u1 direction is irrelevant to z direction. Z coordinate is here, which is related to theta here. So only when theta changes, the z direction changes. Since its generating curve g of x only lies on this xy plane here, we can safely say that the unit normal vector here, unit normal vector on this generating curve, this theta factor does not change in the direction of u1. So we can say that for the direction of u1, we can put that theta is 0, which means we can only deal with unit normal vector field x comma theta equals 0. Okay. However, for the case of u2 direction here, even though the x is fixed here, this u2 direction only changes the theta here. So x is fixed, and then theta changes here. So in this case, the only variable for the unit normal vector field is theta here. Okay. Okay, let's do some computation. Okay, for the case of shape operator on this generating curve to the direction of u1 here, so u1 direction is this direction, and z coordinate it does not contribute. So in this case, the change of unit normal vector field along this direction is irrelevant to theta. So I can plug 0 into theta here, and we'll have x over 4 times square root of 1 minus 3x square over 16, and square root of 1 minus x square over 4 over 1 minus 3x square over 16, comma 0 here. Since sine of 0 is 0, cosine of 0 is 1. Okay, how can I take the unit speed curve gamma of t such that gamma of t equals 0 is the same as g of x, which is x comma square root of 1 minus x squared over 4 comma 0 here. And since it is unit speed, take its derivative and taking its norm, it should have 1, and the direction when t equals 0 of this derivative will be the same as this u1, since u1 is unit vector. Okay. By the way, you can do it by yourself, but by the virtue of the surface of revolution here, actually by taking the normalization of this u1 vector field, we can think that this unit speed curve gamma of t, we take this x variable is a function of t here, and then each gamma of t is nothing but this generating curve here, 1 minus x of t square over 4 comma 0. Okay, and we have to determine its t derivative of this x coordinate to make it as a unit speed curve. So we take a t derivative of this curve, and we'll have let me say x prime denotes derivative with respect to t here, and 1/2 for the denominator there is a square root of 1 minus x squared over 4. For the numerator, we'll have minus 2x x prime over 4 here, comma 0. We take each norm here of t derivative of this gamma curve, and we'll have those twos are cancelled out, and x prime is common factor. Let me take a square first here. So what I have is x prime is square plus each square will have 16 x square x prime square and 1 over 1 minus x square over 4, and we have a common factor which is x prime and its square. So what's left is this one, 1 plus x squared over 16 over 1 minus x squared over 4. And by the calculation, I believe you can do it. It has 1 minus x squared over 4 on its denominator, and it has 1 minus 3x squared over 16 on its numerator. So to make this curve as a unit speed, so we have to multiply the inverse of this square root. So x prime of t, it should be 1 minus square root of 1 minus x squared over 4 over 1 minus 3x squared over 16. Okay? And then you can see that by plug in this x prime value to those two x prime, and you will have t derivative of this unit speed curve will be square root of 1 minus x squared over 4 over 1 minus 3x squared over 16, comma, minus x over 4, and we plug in this square root value to the x prime, and the square root of 1 minus x squared over 4s are cancelled out, and what's left is 1 over square root of 1 minus 3x squared over 16, comma 0. This is the same as the first basis vector of the tangent plane on this generating curve. This is nothing but the u1. So, okay. And then let's say that this unit normal vector lies on this unit speed curve gamma of t, and theta should be 0 for the case of z equals 0 here. And we'll take a t derivative to figure out its directional derivative here. So on the case of gamma of t here, the x coordinate is a function of t here. Okay, we take a derivative with respect to t, and then we'll have by the virtue of fractional derivative, we'll have square of its denominator and take a t derivative. So on this section, x prime means t derivative of x here times its denominator, which is square root of 3x squared over 16 minus x times the derivative of denominator, which is 1/2 1 minus 3x squared over 16 minus 6x x prime. This is a t derivative, let me emphasize, over 16. And then for the second coordinate, we'll have 1/2 times it's a negative 1/2 power, so I'm gonna take a inverse. So square root of 1 minus 3x squared over 16 over 1 minus x squared over 4, and we take a derivative inside of this square root by using the fractional derivative. We take the square of its denominator, and we take a t derivative on the numerator first, and we multiply its denominator minus 1 minus x squared over 4, and take the t derivative on the denominator, which is negative 6 x prime over 16. Okay, this is a little bit messy, but let's do it. First, for the x coordinate, here, let's compute this numerator first here. So 2 and 6 are cancelled, and x prime which is this value, is common. So for the nominator, part, I have a common x prime here. Let me pull out the 1 over square root of 1 minus 3x squared over 16, and I have 1 minus 3x squared over 16. And then for the second term here, 2 minus gives us a plus, and there's a 3 over 16 and x squared and x prime. So plus 3, and x prime is common, so what's left is 3x squared over 16. Okay, and this 1 over square root of 1 minus 3x squared over 16, which I have already pulled out, so those two terms are cancelled. And x prime of t is nothing but this value, but these square root values are cancelled out, and what's left is, this is nothing but square root of 1 minus x squared over 4. No, I'm sorry. They are not cancelled, they are multiplied. So over 1 minus 3x squared over 16. Okay, that looks better. They are not cancelled out. And so the rest thing, which is on the denominator, will have so x coordinate will have 1 over 4. We have another 1 minus 3x squared over 16, so it's square. So this is for x coordinate here. So let's do the same thing for the y coordinate here. So for the y coordinate case, let's do the nominator first. Okay, so on the nominator, I mean this part here. Okay, x prime are the same, and there's a 2 minus sign here. I'm gonna put a plus sign. So let me write x prime. Okay, I'm gonna just do that because there's no square root. So for the nominator part, I have negative 2x x prime over 4 plus 6x cubed x prime over 16. No, it's 4 times 16 is 64. Okay, and then we multiply those two plus 6xx prime over 16 minus 6x cubed x prime over 64. 4 times 16 is 64, and those two terms are cancelled out, and what's left is those two terms, which is negative 2xx prime over 16, which is negative 1 over 8 times x prime here. So okay, So on this case, let me bring it here for the y coordinate here. What's remaining is this part and this part. So 1/2 of square root of 1 minus 3x squared over 16 over 1 minus x squared over 4, and I have 1 minus 3x squared over 16 and each square. And for the nominator part, I have 1 over 8 times x prime here, which is nothing but square root of 1 minus x squared over 4 over 1 minus 3x squared over 16. Okay, in this case, those two factors are cancelled out, and what's left is negative x over 16 times 1 over 1 minus 3x squared over 16 and each square. So for the y coordinate case, we have negative x over 16 times 1 over 1 minus 3x squared over 16 and each square. Okay. Okay, so the shape operator of this one is minus of directional derivative on u1 direction of its unit normal vector, which is on this generating curve here, g of x, is 1 over 4 times 1 over 1 minus 3x squared over 16 and each square, and minus 1 over 16, 1 over 1 minus 3x squared over 16 and each square, comma 0. So obviously, when we express it as a linear expression of u1 and u2, so u2 vector does not contribute, so each coefficient will be 0. And since u1 is this vector, we can figure out that each coefficient, I'm sorry, I missed one vector here. So what I have missed is this vector. This should not be cancelled out, so there must be a square root of 1 minus x squared over 4. So there should be a square root of 1 minus x squared over 4. So the coefficient of this u1 vector will be one quarter times 1 over 1 minus 3x squared over 16 and it's 3/2 power. Okay, so this is our first result. And I'm sorry, I missed one more thing. There's a minus sign here, so I should have changed the sign here. So actually the negative sign inside this derivative does not change a fundamental result. It only makes our lives a little bit convenient, but I have to follow the rules, so there should be a minus sign on this case. Okay, let's do the same thing for the case of U2 vector. For the case of U2 vector, we do need a change of this theta, and the U2 vector on the point of generating curve g of x, it was 0, 0, 1. Here, the direction only changes the z direction, so I'm gonna take the unit speed curve, which has a parameter t, and let me draw a picture here. So let me remind you, there's a generating function g of x here, and we rotated this generating function along this x-axis. Okay, so this y value will be will act like a radius of the circle, and this will be our theta. And as you know, the g of x has a y coordinate, which is square root of x squared over 4. So its radius will be this one. And then the unit speed curve will move along this line. So it does not change its x coordinate, but it do change the value of theta. So gamma of t, we take this gamma of t as for a fixed x, and we'll have its radius and cosine of theta of t, and square root of 1 minus x squared over 4 times sine of theta of t here. So only the theta changes, which is a function of t, and let me take its t derivative of this unit speed curve. It should be a unit speed curve. So take the t derivative, and we have 0 and minus square root of 1 minus x squared over 4 times sine of theta times and theta prime. Here I denote theta prime as a t derivative of theta of t here, and derivative of cosine is minus sine. So I do the same thing for the z coordinate. I have cosine theta times theta prime here. And by taking the norm of this gamma prime, actually let me take its square, and I have square root of theta prime and times 1 minus x squared over 4. Okay, so to become a unit speed curve, this theta prime should be 1 over square root of 1 minus x squared over 4. Okay, this is the first thing. And obviously when t equals 0, gamma of 0 is nothing but x comma 1 minus x squared over 4 comma 0, which lies on this generating curve. Okay, so let's take a directional derivative of this unit normal vector. So for the second case, shape operator on g of x to the direction u2, it's a minus of directional derivative of u2 of the unit speed unit normal vector field when theta is theta of t. And actually the unit speed unit normal vector field lies on this unit speed curve gamma of t. Okay, so let's take a t derivative first here. So in this case, only theta is a function of t here. So hopefully this will not be complicated. So x coordinate, there's no function of t. For the y coordinate, we have square root of is minus is for derivative of cosine here, and then we have this much. And then for the z coordinate, we have the same thing, and cosine of theta and theta prime. For the derivative of sine, so 1 minus x squared over 4 over 1 minus 3x squared over 16. Okay, so evaluate at t equals 0. That means theta becomes 0 here. Okay, theta starts from here on the xy plane. So when you evaluate it on t equals 0, we have 0 here. So the y coordinate does not contribute here. And for the cosine of 0 is 1. So we have theta prime, which is 1 over square root of x squared over 4, which is cancelled out. So what's left is 1 over 1 minus 3x squared over 16. Okay, so by taking each negative sign, we have 0, 0 minus 1 over square root of 1 minus 3x squared over 16. So this has a linear combination of those two orthonormal bases. 0 coefficient for the u1, and since u2 vector is 0, 0, 1, so minus 1 over square root of 1 minus 3x squared over 16 will be a coefficient of u2. Okay, we almost there. For the shape operator, which is a directional derivative of this unit normal vector, so this is more related to normal curvature. because taking a directional derivative whose direction is on the tangent, that will provide the second derivative of this given unit speed curve of gamma of t here. So those two informations contains information about normal curvature, and now we can find the representation matrix representation of this shape operator here, because we have orthonormal basis u1 and u2. So let me say each matrix representation is a capital A, and will have minus 1/4 times 1 over 1 minus 3x squared over 16, and it's 3/2 power and 0 for those two coefficients. And the next one, for the next one, 0 and minus 1 over square root of 1 minus 3x squared over 16. And let me give you a brief comment for finding the orthonormal basis of the tangent vector for tangent vector at this on this generating curve. Here we have a symmetric matrix representation. This is because we have used orthonormal basis. Okay, this is why, because they are orthonormal. So let's say for the shape operator u1, we have a times u1 plus b times u2 here, and say for the shape operator on the direction u2 vector on the generating curve, c times u1 plus d times u2 here. And then we take a inner product, this one with u2 unit vector, and then since this shape operator is self-adjoint, which means I'm not gonna go detail, but here self-adjoint means this equality holds for every tangent vector field u1 and u2. Okay, so in this case, from the first case we have a times u1 plus b times u2. For the second case, we have c times u1 plus d times u2. Okay, and we take inner product with respect to u2. By orthogonality, we get b by taking a inner product with u1 vector. We take a value c here, so they should be the same, and b and c should be the same. That means this should be a symmetry. So all this property comes from orthogonal basis and self-adjoint property of this shape operator L. Okay, so this gives us a good shape of matrix representation. So what is good for symmetric representation? Each eigenvalues, when it is symmetry, is always real. So we don't need to worry about having complex imaginary eigenvalues. So, and then each eigenvalues, it turns out there are two eigenvalues, let's say k1 and k2. Each two eigenvalues are nothing but maximum and minimum value of its normal curvature on the whole direction of this tangent plane on this generating curve, and the multiplication of those two eigenvalues, we define it as a Gaussian curvature here, capital K, can be obtained from determinant of this matrix. So by taking a determinant of this matrix, we get 1/4 times 1 over 1 minus 3x squared over 16 and its square. So this is our first main result. So from this one, as you already know, so the Gaussian curvature at the point P prime, where the x coordinate is square root of 2, is 1/4 times 1 over 1 minus 6 over 16 and its square. And if you compute this one, you have a value 16 over 25. Okay, the remaining thing is to figure out the total curvature on this surface, say surface M here. To figure out the element of area, the A, on the surface of revolution case. So there's a generating curve. We called it the g of x here, and we rotated it through the x-axis by theta. So the area element of this surface of revolution will be this much, and the theta, the infinitesimal element of theta here, in this case the radius will be y here, and then the height, for the height it is light on the xy plane here. So this height will be square of dx plus square of dy. So the area element will be approximated to this rectangle with the height dx squared plus dy and it's square root times y times d theta, because this width is approximated to y times d theta. And then since we know the formula for this generating curve, which is this one, so y is square root of 1 minus x squared over 4, and on this square root we can pull out the dx outside, and we have 1 plus square root of dx and dy, and the y value is nothing but the square root of 1 minus x squared over 4 times d theta. And by the taking x derivative to this y, and we have 1/2 times this calculation we have already seen many times before in this one. So let's take a square on both sides, and we'll have x squared over 16 and over 1 minus x squared over 4. Okay, so 1 plus square root of dy dx will be this one, 1 plus x squared over 16 over 1 minus x squared over 4, which will be 1 minus 3x squared over 16 over 1 minus x squared over 4. Okay, so the element of area will be dx and square root of 1 minus 3x squared over 16 over 1 minus x squared over 4, and square root of 1 minus x squared over 4 times d theta, and the square root of 1 minus x squared over 4s are cancelled out, so what's left is this is nothing but square root of 1 minus 3x squared over 16 times dx d theta. So let's combine all of these. So for the curvature on this generating curve, we have 1/4 times 1 over 1 minus 3 x squared over 16, and it's square. For the element of area, we have square root of 1 minus 3x squared over 16 dx d theta. X from 0 to 4 over square root of 5, and theta goes from 0 to pi over 3. So our maximum theta is pi over 3, because this is a line of z equals square root of 3 times y. This is a pretty solid mathematical problem, and one point of this problem is the integrand is independent of theta, so its total curvature on the surface M, we multiply pi over 3 outside, and we factor out 1/4 outside also, and they are cancelled, so what's left is 1 over 1 minus 3x squared over 16, and it's 3/2 power, and dx, x goes from 0 to 4 over square root of 5. Okay, Okay, so the integrand does not look pretty, but we can do something here. Okay, by the change of variable, so let me change x equals to square root of 3 and 4 over square root of 3 and sine of what to say sine of just theta, sine of phi. It looks better. Okay, where's my phi? Here looks better. To make the inside of parentheses, it looks like 1 minus square of phi here. Okay, so in this case, x goes from 0 to 4 over square root of 5, so sine of phi goes from 0 to square root of 3/5. Okay, so let's say square root of 3/5 is a sine of beta. So for the acute angle beta here, we have hypotenuse square root of 5 and its height square root of 3 and its base square root of 2. Okay, and then I can proceed. So we have pi over 12 and let's take a derivative on both sides. We will have 4 over square root of 3 cosine of phi d phi. Okay, so phi goes from 0 to beta here, and it has a 1 minus square root of phi, and it's 3/2 power times 4 over square root of 3 times cosine phi d phi. Okay, so you know that this value is cube of cosine phi, and this cosine, one cosine is cancelled out, and what's left is I'm gonna pull out this vector 4 over square root of 3, and what I have is integration from 0 to beta 1 over square of cosine phi d phi. And from the equation, famous equation, square of cosine plus square of sine equals to 0. No, I'm gonna just say the derivative of tangent gives us 1 over square of cosine here. So I can find the antiderivative of 1 over square of cosine. It is called the square of secant. So I can do this integration with antiderivative, which is a tangent. Phi goes from 0 to beta. So when I evaluate this one is tangent beta minus tangent 0, and tangent beta is square root of 3/2, and tangent 0 is 0. So the whole value which is left in the end is nothing but this value. So we cancel out some values, and we have pi over 3 times square root of 2. That will be our total curvature, value of total curvature on this curve. Okay, it was a very long journey, and let me wrap up this problem briefly. First of all, to deal with the Gaussian curvature on this surface of revolution, which is a rather special case, we have to parameterize this surface with respect to x and theta here. Theta is for angle of rotation with respect to x-axis, and to figure out its normal vector on its generating curve, which is g of x. It is a generating curve, x comma square root of 1 minus x square over 4 comma 0. By the virtue of the surface of revolution, those two partial derivatives are orthogonal with each other. So that makes us to easily find orthonormal basis of a tangent plane on this generating curve g of x. Okay, and then all the information, geometry information, is contained on the geometry information on this generating curve. And by introducing the shape operator, which is self-adjoint, we figure out the matrix representation of this shape operator, which contains, we believe, which contains information of normal curvature, because the shape operator is essentially a directional derivative of this uninormal vector to the direction of one of basis of tangent plane. Okay, and then from the matrix representation, which was symmetry, because the shape operator is a self-adjoint, and also we have used the orthonormal basis for the tangent plane. Those two conditions makes the representation with respect to this orthonormal basis of the shape operator is symmetry. And in this case, the calculation of determinant, which is a product of two principal curvatures, its geometry meaning is maximum and minimum value of normal curvature. When you search this value of normal curvature, this is a generating curve. It's a point P through the whole direction of this tangent plane. Okay, and their multiplication is called the Gaussian curvature capital K. So by figuring out the formula of Gaussian curvature on this generating curve, we can find total curvature on the surface, which is a surface of revolution, by technique of integration. Okay, that's it. Hopefully it will be helpful. You will have fun. Thank you.